All right, so today we're going to finish up our discussion where we had left off with hyperbolic geometry. Just have a tiny bit more to do, and then we'll be changing gears a little bit. So let me flip to where we were. This has been a pretty long file. We've been continuing. Okay, oops, here we go. So we had some homework. You had done that. We actually looked at this particular P10 exercise, and where were we before? Notes. All right, so we're on the top of this particular page. All right, we had started looking at, or had touched on how we are going to define length in terms in the hyperbolic geometry system. And we had measured it over here at the bottom of this, talking about the cross ratio. And that's where we had left off. I know it's like a week ago now, but that's where we left off, was talking about the cross ratio. And we had made a comment that as the B and the A get closer together, as B gets closer to A, the distance gets closer to 1, and as B gets closer to P, the edge of the circle, the distance approaches infinity. And that's where we had left off, I believe. So we're going to do a couple more things before we leave hyperbolic geometry for other areas. So a definition. Okay. The Poincaré and my writing is really not good today. Length between A and B is defined as follows. So the distance of this segment, if you will, AB, in fact, I'm going to move this. Is the absolute value of the natural log of AB to PQ. And that information was what we defined over here to be the cross ratio. So we could fit that in there if you wanted to be more clear. So a note about that. The distance, we would always hope, between two objects from A to B or B to A are equal. Because the cross ratio, I keep wanting to say cross product, the cross ratio from of AB PQ is 1 over BA to PQ. And the natural log that we have described above, so I'm not going to write it all out, but the natural log here is the same. So those distances are equal, which is what we would want them to be. And we had talked about before, one of the reasons we want to be able to talk about distances is we want to be able to talk about congruences, right? If you don't have distance defined in a way that makes sense, congruences are also going to be defined awkwardly. So by definition, P segments, Poincaré segments, these arcs that we've been working with, AB and CD are P congruent if this way that we've defined distances are equal. So the distance AB is equal to the distance or the length of CD. Which is exactly what we mean by congruent, right? And that's how we define it in terms of Euclidean geometry as well. The congruences happen when we have congruent or equal length segments. I'll actually go to the next slide because then I'll be able to keep the proof on there with it. So let me pause. Does everybody, I know Felipe just came in, but everybody else have this written down at this point? Okay, we'll catch you up, Felipe, after class. Okay, so a fact that we are going to prove is that for C star B, right, so C is between A and B, that if you take the distance from A to C plus the distance from C to B, this will equal the distance from A to C. B, get the right letter here. The letters in the right, I think so. We had a name for this before. What do we call it? Segment addition. So this is the equivalence of the segment addition postulate for Euclidean geometry. We're just using segments that are these arcs now. And we are going to prove this one. So because AB to PQ and the cross ratio of AC PQ and CB PQ are greater than 1, their logs will be positive. Right? The logs are greater than 0. So we're going to drop the absolute values. We're just not going to have to use them. Then the distance A to C plus the distance from C to B will have the following form. So we'll have the natural log by definition of ACPQ plus the natural log of CBPQ. Okay, so tell me what you remember about natural logs, natural log properties. This is a college algebra topic at this point. Do you remember natural log properties? What do you remember, Kelsey?
When you add them and multiply.
Right. So I should be able to rewrite them like this. Right? Okay, so maybe you didn't remember that right off the bat, but does everybody remember that now? That that's a property of logs. Okay, fabulous. All right, now we're going to use the definition of the cross ratio because that's what we've got present here is two cross ratios that are being multiplied, and the log is out in front. So our cross ratios look something like this. AP times CQ over CP times AQ, and then we have CP BQ over BP CQ. And what do you see happen? Yeah, there's some canceling. Can you tell me one that cancels, Hannah? Do you see one? CQ, at least if I had written them neatly, they would both look like CQs. They are supposed to be CQs. Any others that anyone sees? CP. So if I rewrite what's left then, we have AP on top and BQ. And we have AQ on bottom and BP. And that is the same as the natural log of the cross ratio of AB to PQ by definition, which is, again, by definition, the distance AB, the length of the segment AB. So fun college algebra proof in the middle of the And that is exactly where we're going to leave our hyperbolic geometry. Okay?